Look up at the night sky, and you're gazing into a cosmic mystery that defies everything we thought we knew about the universe, the stars, the galaxies, even the empty darkness between them. It's all moving, expanding, but not in the way you might expect. Scientists once believed the universe's expansion would slow down over time, pulled back by gravity's relentless grip. But instead, something bizarre is happening. The universe isn't just growing, it's accelerating, flying apart faster and faster, as if some invisible hand is pushing it outward with unimaginable force. And here's the kicker: we have no idea what that force actually is. We call it dark energy, a name that sounds like something out of a sci-fi novel, but it's very real, and it makes up nearly 70% of everything in existence. Yet, despite its colossal influence, it remains one of the greatest unsolved puzzles in science. Picture this: galaxies, those towering islands of stars, drifting away from each other like ships lost at sea. The farther apart they get, the faster they move, as if space itself is stretching beneath them. It's not just a slow creep, it's a runaway explosion on a scale we can barely comprehend. Imagine blowing up a balloon with tiny dots on its surface. As the balloon inflates, the dots move away from each other. Now, imagine the balloon starts inflating faster and faster all on its own, with no one blowing into it. That's the universe we live in, an ever-accelerating cosmic balloon, and dark energy is the mysterious breath driving it. So why does this matter? Because this isn't just some abstract idea tucked away in a physics textbook. The fate of everything, every star, every planet, even the fabric of reality hangs in the balance. If dark energy keeps pushing the universe apart, what happens in 1 trillion years? Will galaxies vanish over the horizon of space, leaving ours alone in an empty void? Or could this enigmatic force suddenly change its mind, collapsing the cosmos in a dramatic reversal? These aren't just questions for scientists. They're part of the human story, a quest to understand our place in a universe that's full of secrets. And today, we're going to unravel the enigma of dark energy piece by piece to uncover what it might mean for the future of everything we know. Buckle up, because the answers might just bend your mind. Before Edwin Hubble peered through his telescope in the 1920s, most scientists thought the universe was static, a vast, unchanging stage where stars and galaxies simply existed. But Hubble saw something that shattered that view forever. Using the most powerful telescope of his time at Mount Wilson Observatory, he noticed something peculiar about distant galaxies. Nearly all of them were racing away from us, their light stretched into longer, redder wavelengths, a phenomenon we now call redshift. The farther away a galaxy was, the faster it seemed to be fleeing. This wasn't random motion, it was a pattern, and it pointed to one astonishing conclusion. The universe wasn't just big, it was growing, stretching space itself like the surface of an inflating balloon. Hubble's discovery rewrote the rules of cosmology. Suddenly, the idea of a static, eternal universe crumbled, replaced by a dynamic, expanding cosmos with a dramatic origin story. If galaxies were moving apart now, they must have been closer together in the past. Rewind the tape far enough and everything, all matter, all energy, even space and time, would have been compressed into an unimaginably hot, dense point. This was the birth of the Big Bang Theory, a radical idea that suggested our universe had a fiery beginning nearly 14 billion years ago. But Hubble's observations didn't just give us a starting point. They hinted at something even stranger lurking beneath the surface. If gravity was the only force at play, the universe's expansion should have been slowing down over time. Yet, decades later, astronomers would discover the opposite was true. A revelation we'll explore next. For now, though, Hubble's work stands as a turning point, the moment humanity first glimpsed the universe not as a frozen backdrop but as a living, breathing entity still unfolding its story. The more we learn, the more we realize how much we don't know. And that's where the real adventure begins. For centuries, scientists assumed the universe played by gravity's rules, that after the explosive fury of the Big Bang, the cosmic expansion would gradually slow, like a ball rolling uphill against gravity's pull. But in 1998, two teams of astronomers made a discovery so bizarre it turned cosmology upside down. They weren't just studying distant galaxies, they were hunting for cosmic mile markers, special exploding stars called Type 1, a supernova. These stellar explosions always release the same amount of light, making them perfect standard candles to measure vast distances across space. What they found sent shockwaves through labs and observatories worldwide. The most distant supernovae were dimmer than expected, not because they were fading, but because space itself had stretched more than anyone predicted. The universe wasn't just expanding, it was speeding up as if some invisible repulsive force had flipped gravity's script. One team leader, Saul Perlmutter, described the moment of realization as equal parts thrill and terror. His rival team, led by Brian Schmidt and Adam Rees, double-checked their data for months, convinced they'd made a mistake. They hadn't. The implications were staggering. Either Einstein's theory of gravity, the foundation of modern physics, was incomplete, or space contained a mysterious energy that pushed galaxies apart. Most physicists had dismissed Einstein's cosmological constant, a mathematical fudge factor he'd once called his greatest blunder. Now it was back with a vengeance, rebranded as dark energy. The team's findings were so radical they split the Nobel Prize just 13 years later, one of the fastest recognitions in the prize history. Imagine the scene at academic conferences that year. Seasoned theorists clutching their coffee cups, staring at equations that no longer added up. It felt like the floor had dropped out from under us, recalled one astrophysicist. Even the language of cosmology changed overnight. Textbooks still describe the universe's fate as a choice between endless expansion or a big crunch collapse. Suddenly, neither option fit. The universe wasn't just winning against gravity, it was cheating, accelerating on a trajectory no one saw coming. What made this discovery even more unsettling was how ordinary the tools seemed. No futuristic gadgets, just meticulous observations of ancient starlight. Those faint supernovae, erupting billions of years ago, carried a message no one had anticipated. The cosmos wasn't just evolving. It was running away from itself, driven by something we still struggle to name. And that realization that after centuries of discovery, the universe still holds cards close to its chest, is what keeps scientists staring at the night sky with equal parts wonder and humility. Dark energy isn't just another entry in the catalogue of cosmic oddities. It's the dominant force shaping the fate of the universe, yet it's utterly invisible to our telescopes and detectors. Think of it like the wind. You can't see it, but you feel its effects. In this case, dark energy isn't pushing galaxies apart directly. It's stretching the very fabric of space between them, an expansion so relentless that it overpowers gravity's pull. What's wild is that this mysterious energy isn't some rare ingredient. It makes up roughly 68% of the universe's total energy budget. That means for every speck of stars, planets, and gas we can see, there's more than twice as much dark energy filling the voids, driving the cosmos apart. Now here's where things get even weirder. Dark energy isn't the same as its cosmic cousin, dark matter. Both are invisible, but they play completely different roles. Dark matter acts like cosmic glue. Its gravity holds galaxies together, keeping stars from flying apart as they spin. Without it, our Milky Way would have torn itself apart long ago. Dark energy, on the other hand, does the opposite. It's the anti-glue, working against gravity to push the universe into an ever faster expansion. And while dark matter clumps around galaxies like an invisible halo, dark energy seems perfectly smooth, evenly smeared across all of space. It's as if the universe has two hidden hands, one pulling matter together, the other ripping space apart. But what is it really? That's the million-dollar question. The simplest explanation is that dark energy is a property of space itself, what Einstein once called the cosmological constant. Empty space, according to quantum theory, isn't truly empty. It's a seething foam of virtual particles popping in and out of existence, and this quantum buzz might generate a repulsive force that accelerates expansion. But there's a problem. When scientists crunch the numbers, the predicted energy of this quantum vacuum is trillions of times stronger than what we observe. That mismatch is one of the biggest unsolved problems in physics. Another possibility: dark energy isn't constant at all. It could be a dynamic field, evolving over time like an invisible fifth force of nature. Some theories even suggest it might grow stronger, eventually tearing atoms apart in a catastrophic big rip, or it could fade away, letting gravity reclaim dominance. Right now, we just don't know. Every telescope, every deep space survey, every supernova we analyze is hunting for clues to this enigma. Because if we crack the mystery of dark energy, we won't just understand how the universe expands, we'll finally glimpse the ultimate destiny of everything in it. Einstein once scribbled a term into his equations that he would later call his greatest blunder, a mathematical placeholder he labeled the cosmological constant. It was 1917, and the prevailing belief was that the universe sat perfectly still, neither expanding nor contracting. But Einstein's theory of general relativity suggested something unsettling. Gravity should cause the cosmos to either collapse inward or fly apart. Since astronomers insisted the universe was static, he tweaked his equations by adding this fudge factor, a kind of anti-gravity force that counterbalanced gravity's pull, keeping everything in equilibrium. Then came Hubble's bombshell discovery. The universe wasn't static at all, it was expanding. With observational proof in hand, Einstein abandoned his constant, dismissing it as unnecessary. But history has a way of circling back. Decades later, when astronomers found the universe's expansion wasn't just continuing but accelerating, the cosmological constant got a second life. Suddenly, that blunder looked prophetic, a premonition of dark energy written into the math a century before its discovery. Here's the twist: Einstein's constant wasn't about expansion at all. It was a static fix for a static universe, while dark energy is dynamic, an active push against gravity's grip. Yet modern physicists recognize the eerie resemblance. Both concepts describe energy inherent to space itself, a repulsive force woven into the cosmos's fabric. The difference: Einstein's constant was a stopgap. Today's version is a mystery screaming for an answer. Quantum physics adds another layer to the puzzle. Empty space, it turns out, isn't empty. At the tiniest scales, particles flicker in and out of existence, a quantum froth teeming with energy. Theorists once hoped this vacuum energy could explain the cosmological constant, but the numbers refused to cooperate. Calculate the energy density of this quantum foam, and the result is a staggering 120 orders of magnitude too large, enough to rip atoms apart instantly. Clearly, something's missing. This gap between theory and observation keeps physicists awake at night. Maybe dark energy is Einstein's constant in disguise, a faint whisper of quantum noise. Maybe it's something entirely new, a field that shifts over time, or a flaw in our understanding of gravity itself. What's certain is this: that tiny term Einstein scribbled out of embarrassment now holds the key to the universe's ultimate fate. And that's the beauty of science. Sometimes even our mistakes light the way forward. Empty space isn't really empty, not according to quantum mechanics anyway. Even in the deepest void between galaxies, where not a single atom lingers, the fabric of reality crackles with ghostly activity. Particles and antiparticles flicker into existence for fleeting instants before vanishing again, like bubbles in a cosmic foam. This phenomenon, known as quantum fluctuations, suggests that so-called nothingness is actually teeming with energy. And here's where things get mind-bending. Some physicists believe this vacuum energy could be the hidden engine behind dark energy, the very force accelerating the universe's expansion. But there's a glaring problem. When scientists calculate how much energy these quantum fluctuations should produce, the numbers are catastrophically huge, enough to warp space-time with such violence that galaxies would have been shredded before they ever formed. The math predicts a vacuum energy density 10 to the power of 120 times stronger than what we actually observe. That's a 1 followed by 120 zeros, a discrepancy so vast it's been called the worst theoretical prediction in the history of physics. Imagine calculating the weight of a penny and getting an answer heavier than the entire observable universe. That's the scale of our confusion, one possible explanation. Maybe something cancels out most of this energy, leaving behind only a faint residue like the hum of an appliance after the main power shuts off. This leftover trickle could be the dark energy we detect. But what mechanism fine-tunes the cancellation so precisely? No known physics explains it, leading some to propose radical ideas like extra dimensions or undiscovered symmetries in nature. Another twist comes from string theory, which suggests countless possible vacuum states could exist, each with different energy levels. In this multiverse scenario, we might live in a bubble where vacuum energy happens to be unnaturally low, a cosmic accident. But without evidence, it's little more than a tantalizing guess. The vacuum energy hypothesis forces us to confront a humbling truth. Either our understanding of quantum fields is missing a crucial piece, or dark energy is something entirely different. Every attempt to reconcile the numbers feels like trying to fit a square peg into a universe-sized round hole. Yet this frustration is what drives science forward. Because somewhere in the gap between prediction and observation lies a clue, one that might rewrite the rules of reality itself. What if dark energy isn't a fixed feature of the cosmos but something more fluid, more alive? That's the wild idea behind quintessence, a theory that reimagines dark energy not as a static force but as a dynamic field capable of shifting over time. Imagine blowing on a dandelion and watching its seeds drift away, some floating gently, others darting unpredictably. Quintessence suggests dark energy could behave similarly, its influence waxing and waning across billions of years, rather than pressing down on the universe with unchanging intensity like Einstein's cosmological constant. This isn't just wordplay, it's a radical departure from the vacuum energy hypothesis. While the cosmological constant treats dark energy as an immutable property of space itself, quintessence paints it as a cosmic chameleon, a field that evolves alongside the universe. Some models even propose it could interact with matter, subtly changing its behavior as galaxies stretch farther apart. Picture a river that adjusts its current based on the landscape, sometimes flowing lazily, other times rushing violently. Quintessence offers that same flexibility, potentially explaining why the universe's expansion rate doesn't match our quantum vacuum calculations. But how would such a field work? Think of it like an invisible cousin to the Higgs field, which gives particles their mass. Just as the Higgs permeates the cosmos, quintessence could be everywhere, its energy density shifting over eons. Early in the universe, it might have lain dormant, allowing gravity to dominate. Then, as matter spread thin, it could have awoken, pushing galaxies apart with increasing strength. Some theories even suggest it could one day reverse course, flipping from repulsive to attractive, turning the universe's acceleration into a collapse. The name quintessence isn't accidental. It echoes the ancient idea of a fifth element, beyond earth, air, fire, and water, a hidden substance shaping reality itself. Critics point out a glaring challenge: we've never detected such a field. Unlike the Higgs, which announced itself with fanfare at the Large Hadron Collider, quintessence leaves no obvious fingerprints. Proponents counter that its effects might be too subtle for current experiments, revealing themselves only across cosmic distances. Telescopes like the Dark Energy Spectroscopic Instrument are scanning millions of galaxies for clues, hunting for telltale patterns in how structures clump together over time. A slight variation in the expansion rate at different epochs could be the smoking gun, proof that dark energy isn't a constant but a player in an ever-changing cosmic drama. The stakes couldn't be higher. If quintessence is real, it doesn't just tweak our equations, it rewrites the universe's future. A field that weakens over time might let gravity regain control, pulling everything back in a big crunch. One that strengthens could lead to a big rip, shredding galaxies, stars, and even atoms. Or it might simply fade away, leaving the cosmos to expand forever in silence. Right now, all options are on the table. What's certain is this: the quest to understand dark energy isn't just about solving equations. It's about uncovering whether the universe has a heartbeat, a rhythm hidden in the dark, waiting to be heard. The universe's fate hinges on a cosmic tug-of-war between gravity and dark energy. But how this battle ends is still anyone's guess. Picture two possible futures, each more dramatic than the last. In the first scenario, dark energy remains steady, acting as Einstein's cosmological constant. Galaxies keep racing apart, their light stretched into invisibility, until each star system becomes an isolated island in an ever-cooling void. This is the big freeze, a slow, silent end where the universe doesn't explode or collapse, it just fades away, like embers losing heat in an infinite hearth. Stars burn out, black holes evaporate, and space itself grows so vast that no new structures can form. It's not an apocalypse with fireworks, but a whisper, a trillion-year descent into darkness where even time might lose meaning. Now flip the script. What if dark energy isn't constant but grows stronger over time? Instead of drifting apart gracefully, galaxies could be torn apart mid-flight. Stars would shatter first, ripped from their orbits. Then, as space stretches faster than the speed of light, planets would disintegrate, followed by atoms themselves unable to withstand the cosmic tide. This is the big rip, a violent finale where the fabric of reality frays at the seams. It's the difference between a balloon deflating gently and one stretched until it pops. And here's the chilling part: if dark energy's pressure crosses a critical threshold, this could happen in as little as 22 billion years, a blink in cosmic time. So which scenario is more likely? Right now, the big freeze has the upper hand. Observations from telescopes like Hubble and the Dark Energy Survey suggest dark energy's strength has held remarkably steady for billions of years, aligning with Einstein's constant. But the door isn't closed on the big rip. Subtle clues like slight variations in the expansion rate at different epochs could hint that dark energy is dynamic, setting the stage for a future cataclysm. The Euclid Space Telescope, launched in 2023, is mapping billions of galaxies to hunt for these very clues. The stakes couldn't be higher. A big freeze means a lonely but orderly end where the universe simply exhausts its potential. A big rip is chaos incarnate, a demolition of reality itself. And there's a third wildcard option. Dark energy could weaken, allowing gravity to claw back control in a dramatic big crunch. It's a reminder that the universe's story isn't just about where it's been, but where it's hurtling next. Every measurement, every distant supernova we analyze is a vote in this cosmic election. And right now, the ballots are still being counted. Measuring the universe's expansion isn't as simple as stretching a cosmic tape measure between galaxies. To track how fast space itself is stretching, astronomers needed something consistent, a lighthouse in the void that shines with predictable brightness no matter where or when it appears in the cosmos. Enter Type 1, a supernova, the universe's most reliable mile markers. These stellar explosions are so uniform that when one goes off in a distant galaxy, scientists can calculate exactly how far away it is just by measuring how dim it looks from Earth. Here's how it works. A Type 1, a supernova, occurs in a binary star system where a dense white dwarf siphons material from its companion star. Once the white dwarf tips past a critical mass about 1.4 times the weight of our Sun, it detonates in a runaway thermonuclear explosion so powerful it briefly outshines its entire host galaxy. Because this detonation always happens at the same mass threshold, the physics ensures each explosion releases nearly identical amounts of light energy. That consistency is what makes them standard candles, celestial beacons whose true brightness we know, allowing us to gauge their distance by how faint they appear after their light travels across expanding space. But there's a catch. As the universe expands, it stretches the light from these supernovae, shifting it toward redder wavelengths. By measuring this redshift alongside the supernova's apparent brightness, astronomers get two crucial data points: how far away the explosion occurred and how much the universe has stretched since that light began its journey. Compare dozens of these events at different distances, and a pattern emerges: a cosmic speedometer revealing whether expansion is slowing, steady, or accelerating. When those 1998 teams analyzed their supernova, they expected to see the most distant and therefore oldest explosions appearing brighter than standard candle predictions, evidence that the young universe expanded faster before gravity put the brakes on. Instead, they found the opposite. The ancient supernovae were dimmer, meaning they were farther away than anyone predicted. The only explanation: space wasn't just expanding, it was accelerating, carrying those galaxies away faster than light could compensate. Refining these measurements requires near superhuman precision. Modern surveys like the Dark Energy Survey scan thousands of galaxies nightly, hunting for these rare explosions. Each detection gets cross-checked against other distance indicators: cosmic background radiation, galaxy clustering, to rule out errors. The latest data suggests dark energy's strength has held eerily steady for 9 billion years, but even tiny deviations could hint at something stranger lurking in the math. Every flicker of light from these dying stars isn't just a measurement, it's a message from the past, telling us how space itself has bent and stretched since the dawn of time. To understand how dark energy shapes the cosmos, we need to listen to echoes from the universe's infancy, faint whispers trapped in the way galaxies are scattered across space. These patterns, called Baryon acoustic oscillations, are cosmic fingerprints left behind by sound waves that rippled through the hot, dense plasma of the early universe. Picture a stone dropped into a pond, sending out concentric rings. Now imagine that pond is the entire cosmos, and those ripples freeze in place as the universe cools. That's essentially what happened just 400,000 years after the Big Bang, when matter and light finally decoupled, leaving behind a snapshot of those primordial vibrations. Here's why these oscillations matter. As the universe expanded, those frozen waves stretched with it, imprinting a preferred scale about 500 million light-years into the distribution of galaxies. Today, when astronomers map millions of galaxies, they spot this telltale signature: a slight excess of pairs separated by that same cosmic yardstick. It's as if the universe has a hidden grid, a subtle clustering that repeats like a refrain across billions of light years. By measuring how much this pattern has stretched over time, scientists can track the expansion rate with precision, almost like reading tick marks on a cosmic ruler. What makes Baryon acoustic oscillations so powerful is their independence from other methods. Unlike supernova, which rely on the brightness of exploding stars, or redshift measurements that track galaxy motion, these oscillations are anchored in fundamental physics: the interplay of gravity, radiation pressure, and sound waves in the early universe. When the Sloan Digital Sky Survey first detected this clustering pattern in 2005, it provided airtight confirmation of dark energy's influence. The data showed that the universe's expansion began accelerating around 5 billion years ago, exactly matching supernova observations but using entirely different physics. Think of it as cross-examining a witness with two separate alibis. Supernova tell us the universe is accelerating. baryon acoustic oscillations tell us space itself is stretching at a rate only dark energy can explain. Together, they form an irrefutable case, one written in the very architecture of the cosmos. Current projects like the Dark Energy Spectroscopic Instrument are mapping tens of millions of galaxies to refine these measurements, hunting for tiny deviations that might reveal whether dark energy's strength changes over time. Because if those frozen sound waves hold secrets about the past, they might just whisper clues about the universe's ultimate fate too. The faint afterglow of the Big Bang lingers in every direction we point our telescopes, a ghostly microwave whisper known as the cosmic microwave background, or CMB. This ancient light, emitted when the universe was just 380,000 years old, carries encoded secrets about the cosmos's shape, composition, and ultimate fate. Picture it like a fossilized imprint of the infant universe, a snapshot taken when space first became transparent, freezing the conditions of that moment into a pattern we can still decode today. What makes the CMB so revolutionary is its uniformity. No matter where you look, this radiation bathes the cosmos at nearly the same temperature, about 2.7 degrees above absolute zero. But peer closer and you'll spot tiny fluctuations, patches slightly hotter or colder than their surroundings. These imperfections are cosmic gold. They're the seeds of all future structure, the gravitational footholds where galaxies would later cluster. And critically, the size of these fluctuations reveals the geometry of the universe itself. Here's how it works. Light travels in straight lines, but only if space is flat. If the universe were curved like a saddle or a balloon, those primordial photons would bend, distorting the pattern of hot and cold spots we observe. When satellites like COBE and Planck mapped the CMB in exquisite detail, they found a telltale signature. The fluctuations matched predictions for a perfectly flat universe. Not saddle-shaped, not spherical, mathematically flat, like an infinite sheet of paper. But there's a catch. For the universe to be this flat after 14 billion years of expansion, it must have contained just the right amount of matter and energy at birth, a razor-thin balance. Add even a tiny bit more, and space would have curled inward long ago. A tiny bit less, and it would have stretched into an open, hyperbolic shape. The fact that we observe flatness today implies something extraordinary. The universe's total energy density is finely tuned to a critical value within a margin of error of 1%. And that's where dark energy enters the picture. Ordinary matter and dark matter together account for barely 30% of the needed density. The rest, it's the missing 70%, the invisible energy woven into space itself, pushing the universe toward that perfect flatness. Without it, the math simply doesn't add up. The CMB doesn't just suggest dark energy's existence, it demands it, like a puzzle missing its final piece. The most stunning validation came in 2003, when the Wilkinson microwave anisotropy probe analyzed the CMB's polarization patterns. These subtle swirls in the light's orientation revealed how fast sound waves traveled in the early universe, waves that should have moved slower if dark energy hadn't already been subtly at work, gently guiding the cosmos toward its accelerating fate. It's as if the universe left breadcrumbs in its oldest light, clues that only now, billions of years later, we're learning to read. So next time you hear static on an old analog TV, remember, about 1% of that noise is the CMB, the afterglow of creation. And buried in that signal is the universe's deepest confession, that it's filled with a mystery we've only just begun to unravel. Every ripple, every fluctuation is a verse in a cosmic story, one where dark energy isn't just a footnote. It's the force writing the very last chapter. Zoom out far enough and the universe reveals its grand architecture, not as a random scatter of galaxies, but as an intricate web stretching across billions of light years. This cosmic skeleton, known as the large-scale structure, is made up of glittering filaments of galaxies, vast empty voids, and dense clusters where thousands of galaxies huddle together like bees in a hive. But what's truly astonishing isn't just the scale of this structure, it's the invisible hand shaping it. Dark energy isn't just speeding up the universe's expansion, it's sculpting the very framework of reality, determining how matter clumps and spreads over eons. To see this in action, scientists rely on supercomputer simulations, digital time machines that let us watch the universe evolve from its infancy to today. One of the most famous, the Millennium simulation, recreated a virtual cosmos by programming the laws of physics into a colossal supercomputer. The results were mesmerizing. In the early universe, dark matter acted like a gravitational scaffold, pulling ordinary matter into dense knots along its threads. Over time, galaxies formed along these filaments, creating a delicate lacework of light and matter. But dark energy was the wild card. As the simulation ran forward, its repulsive push began to dominate, stretching the cosmic web thinner and faster. Voids grew emptier, filaments stretched longer, and clusters became more isolated, like islands in an ever-widening sea. The real kicker, these simulations match almost exactly what telescopes observe. Projects like the Sloan Digital Sky Survey have mapped millions of galaxies, revealing the same web-like patterns. But here's where dark energy's influence gets eerie. Without it, gravity would have continued pulling galaxies closer, weaving an even denser web. Instead, the voids between filaments are growing faster than the structures themselves, as if space itself is resisting gravity's grip. It's like watching a spider's web being pulled apart from the edges, the silk strands straining as the gaps between them widen. This tug-of-war leaves subtle fingerprints. For example, the way galaxies move within clusters isn't just dictated by gravity. Dark energy's push alters their trajectories, creating peculiar velocities that defy expectations. Even the shape of voids, those cosmic, empty regions, holds clues. In a universe without dark energy, voids would be more spherical, like bubbles in foam. But with dark energy at work, they're stretched into uneven, squashed shapes, as if space itself is being tugged in multiple directions. The most profound implication. Dark energy isn't just a backdrop actor. It's a director shaping the stage on which galaxies form, collide, and fade. As the cosmos accelerates, future civilizations might look up to a sky almost unrecognizable from ours, with galaxies vanishing over an unreachable horizon. Simulations suggest that in 100 billion years, the Milky Way could be the only galaxy left visible in our night sky, the rest carried away by dark energy's inexorable tide. Yet for all its power, dark energy's role in the cosmic web is still full of open questions. Why does it kick in when the universe is already so vast? Could it have influenced the very first strands of the web in the early universe? Every new galaxy survey, every deeper simulation brings us closer to answers, and perhaps to rewriting the story of how the universe builds itself, piece by shimmering piece. What if dark energy isn't the only explanation for the universe's accelerating expansion? Some physicists argue we might be chasing the wrong ghost, that the answer lies not in an unseen force but in our flawed understanding of gravity itself. Enter modified Newtonian dynamics, or MUND, a radical idea that rewrites the rules Einstein and Newton gave us. Instead of invoking dark energy, MUND suggests gravity behaves differently on cosmic scales than our equations predict. Imagine driving a car that inexplicably speeds up when you take your foot off the gas. Instead of assuming an invisible force pushed it, you'd first check if your understanding of how engines work was incomplete. That's MUND's premise, that we've misread gravity's behavior in the vast emptiness between galaxies. One compelling piece of evidence comes from galaxy rotation curves. Stars at the edges of spiral galaxies orbit so fast that, according to Newton's laws, they should fling into space unless unseen mass dark matter holds them in. But MUND tweaks the math, proposing that gravity's pull weakens less sharply over large distances than expected. Suddenly, those fast-orbiting stars make sense without invoking invisible matter. Could a similar adjustment explain cosmic acceleration? Proponents point out that man successfully predicts some galactic motions without dark matter. Yet when applied to the universe's expansion, the theory struggles. It requires additional tweaks like undiscovered gravitational fields, which critics say are just dark energy in disguise. Another alternative, the idea that our universe isn't uniform, that we're sitting in a vast cosmic void, a bubble of lower density stretching billions of light years across. In this scenario, the apparent acceleration might be an illusion. If we're in an underdense region, the surrounding denser universe would exert stronger gravitational pull, making our local space seem to expand faster. Picture a raft drifting toward a waterfall. From the raft's perspective, the water around it appears to rush away, even though it's really being pulled. This inhomogeneous model neatly sidesteps dark energy, but there's a catch. The void would need to be improbably large, contradicting the near-perfect uniformity we see in the cosmic microwave background. Then there's the holographic principle borrowed from string theory, which suggests gravity's weakness compared to other forces hints at a deeper truth, that our three-dimensional universe might be a projection of information encoded on a two-dimensional surface. In this mind-bending framework, dark energy could emerge from quantum interactions at this shadow boundary. It's a tantalizing idea, but like Mund, it lacks definitive experimental proof. Each alternative carries its own baggage. Mund struggles to explain galaxy cluster motions without some form of dark matter. Void models conflict with precise CMB measurements. Holographic theories remain mathematically slippery, yet their value isn't just in being right, it's in pushing us to ask better questions. After all, dark energy itself was once an outrageous idea. Whether any of these rivals eventually dethrone it or simply refine its nature, one thing's certain: the universe still has surprises up its sleeve, and that's what makes the hunt so thrilling. Measuring the universe's expansion rate should be straightforward, like checking the speedometer on a car. But when astronomers compare readings from different cosmic speedometers, they get conflicting numbers and no one can explain why. This growing rift, known as the Hubble tension, is shaking the foundations of cosmology, forcing scientists to question whether they've misunderstood the universe's fundamental physics. One method relies on the cosmic distance ladder, a step-by-step approach that starts with nearby stars. By measuring the flicker of Cepheid variable stars and the brightness of Type Ia supernova, astronomers can climb rung by rung to gauge distances across billions of light years. This technique gives us a Hubble constant, the universe's expansion rate, of around 73 kilometers per second per megaparsec. That means for every million parsecs, about 3.3 million light years, a galaxy is from us. It appears to recede 73 kilometers per second faster. But there's another way to measure the Hubble constant, by studying the cosmic microwave background, the afterglow of the Big Bang. When the Planck satellite mapped the CMB's tiny temperature fluctuations, it allowed scientists to extrapolate the expansion rate backward using our best models of cosmic evolution. The result, a Hubble constant of 67 kilometers per second per megaparsec, nearly 10% lower than the distance ladder value. At first, astronomers assumed someone had made a mistake. Maybe the supernova measurements were off or the CMB analysis missed something. But as years passed and teams cross-checked their data, the gap refused to close. Worse, new techniques like using gravitational lensing or the motions of merging neutron stars kept splitting the difference, landing somewhere between the two conflicting numbers. The tension isn't just persisting, it's growing stronger with every observation. This discrepancy isn't just a quirk of measurement. If the CMB's lower value is correct, it implies dark energy's influence has changed over time, growing stronger as the universe aged. But if the distance ladder's higher number holds, it could mean undiscovered particles flooded the early cosmos, altering its expansion history. Some theorists speculate we're seeing cracks in our understanding of gravity, or that dark energy isn't a constant but a dynamic field with surprises up its sleeve. Imagine two clocks, both impeccably crafted, one running slightly faster than the other. You'd assume one is broken unless time itself flows differently in different places. That's the scale of this puzzle. The Hubble tension isn't just about numbers, it's a hint that the universe might be playing by rules we haven't discovered yet. And until we solve it, every model of cosmic fate, from a big freeze to a big rip, rests on shaky ground. Could our universe's puzzlingly perfect dark energy density be a cosmic accident, one outcome among infinite others in a vast multiverse? This provocative idea, known as the anthropic principle, suggests that if countless universes exist, each with different physical constants, we inevitably find ourselves in one where conditions allow life to arise. Picture a cosmic lottery where universes bubble into existence with random vacuum energies. Most might collapse instantly or expand too rapidly for galaxies to form. But in rare Goldilocks zones like ours, dark energy's value sits just right, weak enough to let stars and planets emerge, yet strong enough to drive the expansion we observe. String theory adds fuel to this speculative fire. Its mathematical framework allows for an eye-watering 10 to the power of 500 possible vacuum states, each representing a universe with distinct physics. In this landscape scenario, dark energy's oddly small value isn't a fluke but an inevitability, a single ticket drawn from a near-infinite stack. The catch: we can't observe these alternate realities, making the multiverse hypothesis frustratingly untestable with current tools. Yet some theorists argue that gravity waves from cosmic inflation or patterns in the CMB might one day reveal fingerprints of neighboring universes. Critics counter that invoking a multiverse to explain dark energy feels like a cop-out, a way to dodge deeper questions about why our universe's constants appear so finely tuned. But consider an analogy. If you stumbled upon a pocket watch in the desert, you wouldn't assume it assembled itself by chance. You'd infer a watchmaker. The multiverse idea flips this logic. If infinite watches exist in infinite deserts, one is bound to keep perfect time. Our universe might be that watch, its dark energy value no more special than Earth's distance from the Sun. A wilder twist comes from quantum mechanics. Some interpretations suggest that every quantum decision spawns branching realities, meaning dark energy's value could vary not just across distant universes, but within infinite versions of our own cosmic timeline. Imagine a tree where each branch represents a universe where dark energy is stronger, weaker, or absent entirely. We're simply on the branch where life could take root. The stakes are cosmic. If dark energy were slightly stronger, galaxies would have been torn apart before life could evolve. Slightly weaker, and gravity might have crushed the cosmos back into a singularity. That our universe avoided both extremes seems miraculous unless, of course, it's just one roll of the dice in a casino with endless tables. Until we find evidence for other universes, this remains a dazzling hypothesis. But it forces us to confront a humbling possibility. The force shaping our universe's fate might not be unique at all, just one note in an infinite symphony of realities. The quest to unmask dark energy is entering its most thrilling chapter yet, with a new generation of telescopes poised to scan the cosmos like never before. Leading the charge is the European Space Agency's Euclid spacecraft, a cutting-edge observatory launched in 2023 with one audacious goal: to create the largest, most precise 3D map of the universe ever made. Euclid's razor-sharp vision surveys billions of galaxies across 10 billion light-years, measuring their shapes and positions with microscopic accuracy. But here's the genius part: it's not just cataloging stars. By tracking how galaxy clusters distort light around them, a phenomenon called weak gravitational lensing, Euclid can trace the invisible scaffolding of dark matter, and by extension, map how dark energy has warped the cosmic web over eons. It's like watching shadows on a cave wall to deduce the shape of the object casting them, except the object is the vast, unseen force dictating the universe's fate. Hot on Euclid's heels is NASA's Nancy Grace Roman Space Telescope, set to launch by 2027. Dubbed the Mother of Hubble for her pioneering role in space astronomy, Roman's namesake telescope carries a dark energy hunter's toolkit. Its wide-field instrument boasts a field of view 100 times larger than Hubble's, allowing it to capture sweeping panoramas of the sky in infrared, perfect for spotting distant supernovae and quasars whose light has been stretched by cosmic expansion. Roman will also study Baryon acoustic oscillations, those frozen sound waves from the early universe, with such precision that it could detect minute changes in dark energy strength across billions of years. Together, Euclid and Roman form a tag team of unprecedented power, one mapping the universe's structure in visible light, the other probing its infrared shadows, their data cross-checked to weed out errors. But the innovation doesn't stop there. Earth-based observatories are joining the hunt with colossal new instruments. The Vera C. Rubin Observatory, perched in Chile's arid mountains, will begin the legacy survey of space and time in 2025, a decade-long project imaging the entire southern sky every few nights. Its 3,200-megapixel camera, the largest ever built, will spot subtle changes in galaxy motions, potentially revealing if dark energies push varies over time. Meanwhile, the Dark Energy Spectroscopic Instrument in Arizona is measuring the redshifts of 35 million galaxies, reconstructing the universe's expansion history with pixel-perfect detail. What makes these missions revolutionary isn't just their scale, it's their synergy. Euclid's lensing maps Roman's supernova, Rubin's time-lapse sky surveys, and Daisy galaxy spectra will converge into a single, multi-wavelength portrait of dark energy's influence. If dark energy is truly a cosmological constant, these observations will pin down its value with razor-thin margins of error. If it's something stranger, a dynamic field like quintessence, the data could reveal its subtle ebbs and flows. And if discrepancies emerge, like the Hubble tension deepening, it might hint at physics beyond Einstein, a paradigm shift waiting in the wings. The stakes are cosmic. These missions could either cement our current understanding of dark energy or blow it wide open, revealing layers of complexity we've yet to imagine. Picture it as a detective story where the clues are written in starlight, and the culprit dark energy leaves fingerprints on everything but remains just out of sight. With every byte of data these telescopes beam back, we're not just filling gaps in our knowledge, we're rewriting the story of the universe one observation at a time. The answers won't come overnight, but one thing's certain: the golden age of dark energy discovery has only just begun. While space telescopes like Euclid and Nancy Grace Roman get much of the spotlight, some of the most ambitious dark energy detective work is happening right here on Earth, where massive ground-based observatories are turning their gaze skyward to decode the universe's deepest secrets. At the forefront is the Vera C. Rubin Observatory, perched high in Chile's Atacama Desert, a facility so powerful it will photograph the entire southern sky every few nights for a decade. Its centerpiece, the largest digital camera ever built, a 3.2 gigapixel behemoth so sensitive it could spot a golf ball on the moon. But Rubin isn't just snapping pretty pictures. Its legacy survey of space and time will track tens of billions of galaxies, watching how their positions shift over years as dark energy stretches the cosmos beneath them. What makes Rubin's approach revolutionary is its sheer scope. Traditional telescopes might study a few thousand galaxies at a time. Rubin will catalog billions, stitching together a time-lapse movie of the universe on a scale never before attempted. Each snapshot captures subtle distortions in galaxy shapes caused by dark matter's gravitational lensing, revealing how dark energy alters the cosmic web's architecture over time. Imagine trying to measure how quickly a forest grows by studying a single tree. Now imagine having a drone fleet that maps every tree, every branch, every leaf across millions of acres day after day. That's the leap. Rubin represents a tidal wave of data that could finally pin down whether dark energy's strength changes as the universe ages. But Rubin isn't working alone. Across the globe, the Dark Energy Spectroscopic Instrument in Arizona is taking a different approach. Instead of broad sky surveys, DAISY focuses on precision spectroscopy, splitting the light from 35 million galaxies and quasars into rainbows to measure their redshifts with exquisite accuracy. This allows scientists to reconstruct a 3D map of the universe's large-scale structure, tracing how baryon acoustic oscillations, those frozen sound waves from the early cosmos, have stretched over billions of years. When combined with Rubin's lensing data, these two projects create cross-verified insights, like detectives comparing fingerprints from separate crime scenes to confirm a suspect's identity. Then there's the Square Kilometre Array, a sprawling radio telescope network under construction in South Africa and Australia. When completed, its thousands of dish antennas will listen for hydrogen gas emissions from galaxies so distant their light has traveled for billions of years. By mapping hydrogen's distribution across cosmic time, the SKA could uncover whether dark energy's push has altered the rate at which galaxies form, a subtle clue about whether this force interacts with matter in ways we've yet to imagine. Ground-based observatories have one crucial edge over their space-based cousins: they can grow. Upgrades to instruments like the Subaru telescope in Hawaii or Europe's extremely large telescope, set to peer into the cosmos by 2028, let scientists adapt as new questions emerge. If Rubin's data hints that dark energy behaves differently in certain regions of space, these telescopes can pivot to investigate, something far harder to do with satellites once they're launched. It's this flexibility combined with raw observing power that makes Earth's high-altitude outposts indispensable in the hunt, yet the challenge is immense. Earth's atmosphere blurs starlight, forcing telescopes to employ adaptive optics deformable mirrors that adjust 1,000 times per second to cancel out atmospheric turbulence. Even then, weather, light pollution, and the simple fact that half the sky is always below the horizon limit what ground-based tools can see. That's why this isn't a competition between Earth and space observatories, but a collaboration. Each fills gaps in the other's vision, together constructing a more complete portrait of dark energy's shadowy influence. The data deluge from these projects will be staggering, petabytes upon petabytes of images and spectra, more than any single team could analyze. That's where machine learning steps in, with algorithms trained to spot patterns human eyes might miss. Already, AI has uncovered strange symmetries in galaxy distributions that could hint at dark energy's fingerprints, and as Rubin and DAISY come online, these digital assistants will become even more vital. We're on the brink of a new era in cosmology, one where the question isn't just whether dark energy exists, but how it operates, whether it's a constant force or something stranger, a field that fluctuates like the tides. With every galaxy mapped, every distortion measured, we're inching closer to answers that could rewrite our understanding of reality itself. And it all starts here, on the windswept mountaintops where humanity's grandest machines stare upward, searching for clues in the dark. To understand how dark energy shapes the cosmos across billions of years, scientists don't just observe the universe, they rebuild it inside supercomputers. These aren't your average laptops. We're talking about machines like Frontier at Oak Ridge National Laboratory, capable of performing more than a quintillion calculations per second. With that raw power, cosmologists can simulate the entire evolution of the universe from its fiery birth to the present day, tweaking the rules to see which version best matches reality. It's like running a million alternate histories of the cosmos, each with different dark energy properties, to find the one where the virtual sky looks identical to our own. One groundbreaking example is the Millennium simulation, which recreated a virtual universe spanning billions of light years. Starting with the smooth soup of matter just after the Big Bang, researchers let gravity and dark energy duke it out in digital space. The results were stunning. Filaments of galaxies emerged, weaving a cosmic web that mirrored actual telescope surveys. But here's where dark energy's influence became undeniable. In runs where dark energy was absent, gravity kept pulling matter into ever denser knots, creating far more galaxy clusters than we see. When dark energy was added, its repulsive push stretched space between filaments, diluting the web into the sparser structure we observe today. These simulations don't just show us what happened, they reveal why. Take the timing problem. Observations suggest dark energy became dominant around 5 billion years ago, but why then? Simulations demonstrate that as the universe expanded, matter grew more diffuse, weakening gravity's grip until dark energy's steady push could take over. It's like a tug of war where one team gradually loses strength, not because their opponents pull harder, but because their own arms tire. The latest simulations go even further, testing wilder ideas like phantom dark energy, a hypothetical variant that grows stronger over time. In these scenarios, galaxies aren't just carried apart, they're shredded in a future big rip. Their stars, planets, and even atoms torn asunder. While extreme, these models help scientists identify which signatures to hunt for in real data. If Euclid or Rubin spots galaxies drifting apart faster than expected, it could hint at phantom energy's presence. What's truly remarkable is how these digital universes are refining our questions. When early simulations struggled to match observed galaxy shapes, theorists realized dark energy might subtly alter how galaxies spin within clusters. Newer models now include this effect, yielding virtual skies nearly indistinguishable from Hubble's deepest fields. It's a feedback loop of discovery. Simulations reveal gaps in our knowledge, telescopes gather data to fill them, and improved models push the cycle forward. Yet challenges remain. Simulating every star in every galaxy is impossible. Even Frontier must approximate small-scale physics. That's where zoom-in techniques help, focusing computational muscle on single galaxies while treating the wider cosmos in broad strokes. Another hurdle, dark energy's potential interactions with dark matter, a possibility that could rewrite cosmic evolution. Upcoming simulations will test these exotic couplings, searching for matches to anomalies like the Hubble tension. As supercomputers grow more powerful, so does our ability to peer into the universe's possible fates. Will dark energy's grip tighten, leading to that catastrophic big rip? Or will it fade, allowing gravity to reclaim control? Every simulation is a test flight for these ideas, a digital crystal ball showing us versions of tomorrow. And with each run, we're not just predicting the future, we're learning how to read the universe's hidden rules, one line of code at a time. Phantom energy isn't just another variation of dark energy, it's a nightmare scenario lurking in the equations of cosmology. Unlike the steady push of Einstein's cosmological constant, phantom energy grows stronger over time, its repulsive force intensifying as the universe expands. Think of it like a car accelerating downhill with no brakes. At first, the speed feels manageable, but soon the momentum becomes unstoppable, hurtling toward disaster. If this extreme form of dark energy exists, it wouldn't just gently stretch the cosmos apart, it would tear everything to shreds in an event so violent scientists call it the Big Rip. Here's how it could unfold. Right now, dark energy's grip is subtle. Galaxies drift apart, but their structures hold firm. With phantom energy, that changes. As space expands faster and faster, gravity's glue weakens. First, galaxy clusters would be ripped apart, their member galaxies flung into the void. Then, individual galaxies themselves would unravel, stars stripped away like leaves in a hurricane. But the horror doesn't stop there. In the final moments, phantom energy's strength would overcome the very forces holding atoms together. Planets, rocks, even molecules would disintegrate, dissolving into a mist of fundamental particles as space itself fractures. The universe wouldn't just fade into darkness, it would explode into oblivion. The math behind this scenario is as chilling as it is elegant. Phantom energy violates what's called the strong energy condition, a rule stating that gravity should always pull matter together under normal circumstances. But in this case, the repulsive force doesn't just counteract gravity, it overwhelms it, growing denser as space expands, a feedback loop of cosmic destruction. Some models suggest this could happen in as little as 22 billion years, a blink on cosmological timescales. What makes phantom energy so unsettling isn't just its apocalyptic endgame, it's how little we'd see it coming. Unlike other cosmic doomsdays like the heat death of the universe, the Big Rip wouldn't give civilizations eons to prepare. Right until the final moments, stars might still shine, planets might still orbit, life might still thrive, until, suddenly, the fabric of reality itself gives way. Could this really happen? Observations so far suggest dark energy behaves like a cosmological constant, its density stable over time, but the margin of error in our measurements leaves room for doubt. If future telescopes detect even a slight increase in dark energy's strength over billions of years, phantom energy moves from theoretical horror story to plausible fate. The universe is under no obligation to make sense to us, nor to end in a way we find comforting. Phantom energy forces us to confront an uncomfortable truth. The cosmos might not just fade away, it could unravel violently without warning. And that possibility, however remote, is enough to send a shiver down the spine of anyone who gazes up at the night sky and wonders what lies ahead. Dark energy's relentless push doesn't just stretch space, it could warp time itself, twisting the universe's clock until the far future becomes a frozen, infinite moment. Picture a river flowing toward a waterfall. At first, the current moves steadily, carrying everything forward at a familiar pace. But as the water nears the edge, it accelerates violently, churning into chaos. Now imagine that river is time, and the waterfall is a universe dominated by dark energy's exponential expansion. In this eerie scenario, the flow of time wouldn't just slow down, it might fracture entirely, leaving distant galaxies trapped in a state of perpetual stillness. This isn't science fiction. Einstein's theory of relativity binds space and time into a single fabric, meaning dark energy's grip on one inevitably alters the other. As cosmic expansion accelerates, the space between galaxies becomes a vast, ever-widening desert. Light from those receding galaxies must cross that growing void, its wavelength stretched so thin that signals eventually fade into undetectable whispers. But the real twist for hypothetical observers in those distant futures, time itself would appear to grind to a near halt. Here's why: when expansion outpaces light's ability to bridge gaps, events beyond a certain horizon become unknowable. No signals can reach us, no causality connects us. It's as if those regions freeze in time from our perspective. Take a hypothetical civilization 10 trillion years from now, huddled around the last surviving stars in an otherwise empty galaxy. As dark energy accelerates, their night sky would grow darker by the eon. Neighboring galaxies would vanish first, their light redshifted into oblivion. Then cosmic background radiation, the afterglow of the Big Bang, would dim beyond detection. Eventually, even their own galaxy's outskirts would fade from view, stranding them in an island of visibility shrinking at an exponential rate. For them, time wouldn't just feel lonely, it would become meaningless. With no external events to mark its passage, their universe's clock might as well stop ticking. But here's where physics gets truly surreal. Some theories suggest dark energy's influence could fray the fabric of causality, the chain of cause and effect that structures reality. In a universe stretched too thin, particles may lose the ability to interact entirely, severing the threads that bind events together. Without causality, the concept of before and after collapses. It's like a film reel where each frame exists independently, unconnected to the next. Distant regions of space wouldn't just be unreachable, they'd exist in a state of temporal isolation where time flows at rates unlinked to our own. The implications haunt the edges of cosmology. If dark energy alters time's flow, could it also warp our understanding of entropy, the universe's slide toward disorder? Normally, entropy ensures time has a clear direction, like an arrow shot from past to future. But in a dark energy-dominated era, the arrow might shatter. With galaxies too far apart to exchange energy or information, entropy could plateau, leaving the universe in a strange, stagnant equilibrium. No new stars would form, no heat would transfer, just an endless, featureless drift toward colder, darker stillness. Yet amid these mind-bending possibilities, a deeper question lingers. Does time itself require change to exist? Ancient philosophers like Zeno argued motion was an illusion, while modern physics treats time as a dimension woven into space's fabric. Dark energy forces us to confront whether time can still pass in a universe where nothing happens, where expansion has erased all visible change. The answer might lie in quantum gravity, a theory still beyond our grasp, where time emerges from something more fundamental. For now, these ideas remain at the frontier of speculation, teased by equations but untested by observation. But that's the paradox of dark energy. Though it shapes the universe's destiny, its full effects won't unfold for eons. By the time they do, there may be no one left to witness them. The ultimate fate of time might be a riddle whispered into an endless void, a final cosmic joke with no one around to hear the punchline. Dark energy doesn't just defy our equations, it shatters our intuition about what it means for space to be empty. For centuries, the void between stars was thought to be just that, a void, an absence of anything substantial. But dark energy flips this idea on its head. The nothingness of space isn't passive or inert, it's dynamic, thrumming with a repulsive force that shapes the destiny of everything. This revelation forces us to confront a profound question. If empty space isn't truly empty, then what is it? The answer might rewrite not just cosmology, but philosophy itself. Consider the ancient debate over the nature of nothingness. Greek philosophers like Parmenides argued that true void was impossible. Reality had to be a plenum, entirely filled with something. Later, Newton envisioned space as a static stage, while Leibniz saw it as merely the arrangement of objects. Dark energy drags this debate into the modern era, suggesting space isn't just a container for matter, but an active participant in the cosmic drama. It's as if the universe itself is breathing, exhaling galaxies into the darkness with each passing moment. This challenges our very definition of existence. Quantum mechanics already taught us that a vacuum seethes with virtual particles, but dark energy adds another layer. Space isn't just bubbling with potential, it's pushing. It's as though the universe has a hidden heartbeat, a rhythm we're only now beginning to sense. Some theorists even speculate that dark energy could be a manifestation of deeper, uncharted physics, a shadow of extra dimensions or a relic from before the Big Bang. The unsettling truth, we might be like ants trying to comprehend the ocean, glimpsing only ripples of a reality far stranger than we've dared to imagine. Then there's the existential weight of dark energy's role in the universe's fate. If it continues to accelerate expansion, the cosmos could end not with a bang or a whimper, but with a slow, inexorable unraveling. Galaxies will vanish beyond an unreachable horizon, stars will blink out, and eventually, even atoms may be torn apart. In this light, dark energy isn't just a scientific curiosity, it's the architect of eternity, silently scripting the final chapters of reality. Yet amid these grand stakes, dark energy humbles us. For all our knowledge, we're still grasping at shadows, trying to decode a universe that operates on rules we've only partly uncovered. Whether it's Einstein's cosmological constant, a dynamic field like quintessence, or something beyond our current theories, dark energy whispers a tantalizing promise: the cosmos still has secrets to spill. And that's what makes this more than a physics problem. It's a mirror held up to our own curiosity, reflecting how much we've learned and how much remains wondrously unknown. One of the biggest misconceptions about dark energy is that it's some kind of cosmic force actively pushing against gravity, like an invisible hand shoving galaxies apart. The truth is far stranger. Dark energy doesn't push anything in the traditional sense. Instead, it's a property of space itself, a kind of latent tension woven into the fabric of reality that causes the universe to stretch faster over time. Gravity still works exactly as Einstein predicted. It's just that on cosmic scales, dark energy's influence becomes dominant, like a rising tide lifting all boats regardless of their anchors. Another myth, that dark energy is something we could detect directly, like a particle or a wave. Unlike dark matter, which reveals itself through gravitational tugs on visible matter, dark energy leaves no such fingerprints. Its presence is inferred entirely through its effect on the universe's expansion. Think of it like the wind in a vast, dark plain. You can't see it, but you watch as distant lanterns, in this case, supernovae and galaxies, drift farther apart at accelerating speeds. The evidence is indirect but overwhelming, written in the redshift of ancient starlight and the eerie uniformity of the cosmic microwave background. Then there's the idea that dark energy is some exotic anti-gravity force. This misunderstanding likely stems from Einstein's cosmological constant, which he initially introduced to balance gravity's pull and keep the universe static. But dark energy isn't the opposite of gravity. It's an entirely different phenomenon. Gravity pulls matter together based on mass. Dark energy alters the very geometry of space, creating more space as time passes. It's not a tug of war between two forces. It's more like the stage itself expanding beneath the actors' feet, making their distances grow without anyone taking a step. Perhaps the most persistent myth is that dark energy is a recent discovery, a sudden plot twist in the universe's story. In reality, its seeds were planted the moment the Big Bang occurred. For billions of years, gravity dominated as matter clustered into galaxies and filaments. Only when the universe grew large enough and matter sparse enough did dark energy's subtle push overtake gravity's grip. We didn't notice it sooner because its effects take cosmic time to manifest, like a slow-motion avalanche finally gaining speed. The beauty of dark energy lies in its elusiveness. It doesn't interact with light or matter. It doesn't clump or cluster. It simply is a silent architect reshaping the cosmos one stretch of space at a time. And that's what makes it so fascinating. It's not just a mystery we haven't solved. It's a reminder of how much the universe still has to teach us, hidden in plain sight. Hollywood loves a good cosmic mystery, and dark energy's eerie invisibility makes it the perfect plot device for sci-fi spectacle. Take Interstellar, where the crew's journey hinges on manipulating space-time, but the film swaps real dark energy for a black hole's gravitational time dilation. It's a clever sleight of hand, using genuine physics to heighten drama while sidestepping the slower, subtler truth. Dark energy doesn't warp time like a Hollywood blockbuster. It rewrites the universe's fate over eons like a slow-motion avalanche. Games, too, stretch dark energy into fantastical shapes. In Mass Effect, the titular effect harnesses a fictional element called ESO to reduce mass, enabling FTL travel. While real dark energy doesn't bend mass, the idea echoes a tantalizing what if. Could we ever tap into this cosmic force? The answer, sadly, is no. Dark energy's uniformity means it can't be bottled or weaponized like ESO. It's less a tool and more like the background hum of reality itself, indifferent to human ambition. Books often get closer to the existential dread dark energy inspires. Neil Stephenson's Anathema imagines monks preserving knowledge as the universe accelerates toward dissolution, while Greg Egan's Diaspora explores civilizations fleeing entropy's grip. These stories grasp the philosophical weight of cosmic expansion, the idea that all structure, all meaning might one day be erased by an indifferent void. It's a theme that resonates because it's rooted in real science, even if the timelines are compressed for drama. Then there's the outright myth-making. Marvel's Doctor Strange conflates dark energy with magical forces, while Destiny's video game lore treats it as a weaponizable energy source. These versions are pure fantasy, but they reveal something telling. When reality's truths are too complex or slow-moving, we reinvent them as immediate, visceral threats. Dark energy is apocalyptic just on a timescale that dwarfs human imagination. The gap between fiction and reality isn't a flaw, it's a testament to dark energy's mystique. Filmmakers and writers aren't wrong to dramatize it, they're answering a primal urge to personify the impersonal, to give shape to the force that will one day unmake the cosmos. But the real story is far stranger, a universe where emptiness isn't passive, where nothing is the most powerful thing of all, the most humbling thing about dark energy. Dr. Priya Natarajan leans forward, her eyes alight with the thrill of the unknown. We're standing at the edge of a cliff, staring into the dark, and every tool we've built gives us a different answer. As a Yale cosmologist, she's spent decades mapping the invisible scaffolding of the universe, yet dark energy remains her greatest puzzle. Some days I'm convinced it's vacuum energy, Einstein's cosmological constant, resurrected. Other days I think we're missing something fundamental, like gravity behaving differently on cosmic scales. Across the Atlantic, Dr. Carlos Frenk chuckles into his coffee. When I was a student, we joked that cosmology was the science of two numbers, Hubble's constant and the density of the universe. Now we've got a full-blown identity crisis. As a key architect of the Millennium simulation, he's seen dark energy's fingerprints in supercomputer models, but the real-world data keeps throwing curveballs. The Hubble tension isn't just a discrepancy, it's a screaming alarm that our models are incomplete. Maybe dark energy evolves, maybe there's a fifth force. Or maybe, he grins, we're all wrong and the universe is laughing at us. Then there's Dr. Elaine Wang, who studies baryon acoustic oscillations with the precision of a cosmic cartographer. People ask, how can you study something invisible? But that's the beauty of it. Dark energy isn't hiding, it's written into the distances between galaxies, the way they cluster, even the silence of the voids. Her team's latest maps reveal anomalies, hints that dark energy's push might vary across space-time. What if it's not a uniform force? What if it's patchy, like weather in the cosmos? That would upend everything. And then there are the iconoclasts. Dr. Pavel Krupa, a vocal critic of dark energy, argues from his Bonn lab, we're so wedded to Einstein's gravity that we've invented an invisible component to save it. What if the real breakthrough isn't finding dark energy but realizing we don't need it? His controversial modified gravity theory draws both applause and eye rolls, but he's unapologetic. Science advances when we question dogma. If dark energy were a particle, we'd have found it by now. Back at Princeton, Dr. David Spergel, who helped decode the cosmic microwave background's whispers, strikes a cautious note. Dark energy could be the ether of our time, a placeholder for deeper physics. Remember, the ether wasn't wrong, it was a bridge to relativity, his hunch. The answer lies in quantum gravity. We're trying to describe dark energy with half a theory, like playing chess without knowing the rules of the pieces. The through line, a delicious collective unease, as Dr. Natarajan puts it. The universe is giving us a pop quiz and we're all scrambling for the right equations. But that's what makes this golden age of cosmology so exhilarating. Every I don't know is a new frontier. You don't need a PhD to help uncover the secrets of dark energy. Some of the most groundbreaking discoveries in cosmology start with ordinary people staring at galaxies on their laptop screens. Projects like Galaxy Zoo have turned citizen science into a powerhouse for astronomy, harnessing the collective curiosity of volunteers worldwide to sift through mountains of data that even supercomputers struggle to interpret. The premise is simple. You log in, scan images of distant galaxies, and classify their shapes: spiral, elliptical, or irregular, but the impact is anything but small. These classifications help scientists map the universe's large-scale structure, tracing how dark energy twists and stretches the cosmic web over billions of years. Take the case of Hanny's voorwerp, a bizarre green blob of gas discovered in 2008 by Dutch schoolteacher Hanny van Arkel while she was classifying galaxies on Galaxy Zoo. At first, astronomers had no idea what it was, just that it didn't match any known celestial object. Turned out, it was a ghostly echo of a quasar's light, illuminating an intergalactic gas cloud long after the quasar itself had faded. Discoveries like these prove that human eyes, especially those untrained to expect only the normal spot anomalies algorithms, might overlook, and in the hunt for dark energy's fingerprints, every oddity matters. The beauty of these projects lies in their scalability. Telescopes like the Vera C. Rubin Observatory will soon flood scientists with hundreds of terabytes of data nightly, more than professional astronomers could analyze in lifetimes. But with thousands of volunteers pitching in, patterns emerge faster. For instance, by counting how many galaxy clusters exist at different distances, citizen scientists help measure how dark energy alters the universe's expansion rate over epochs. It's like taking a census of cosmic neighborhoods across time, and each click of spiral or merging adds a crucial data point. Beyond Galaxy Zoo, platforms like Zooniverse host dark energy explorers, where users flag subtle distortions in galaxy shapes caused by gravitational lensing, a key tracer of dark matter's distribution, which in turn reveals dark energy's influence. There's even Space Warps, a project that trains volunteers to spot the warped light of galaxies bent by invisible mass. These tiny distortions, when mapped across millions of galaxies, expose how dark energy reshapes the universe's scaffolding. What's thrilling is how accessible it all is. You might be sipping coffee at home, scrolling through galaxy images on your phone, and suddenly realize you're the first person ever to notice a peculiar cluster or a rare collision. That's the magic of citizen science. It democratizes discovery, turning curiosity into tangible progress. And in a field where the biggest questions, like the nature of dark energy, remain unanswered, every pair of eyes helps. After all, the next cosmic breakthrough might not come from a high-powered lab. It might come from you, spending billions of dollars to probe the mysteries of dark energy. While hunger, disease, and climate crises plague our planet might seem like cosmic-scale negligence, a betrayal of urgent human needs in favor of abstract curiosity. But this tension between earthly survival and celestial exploration isn't new. When Galileo pointed his telescope at Jupiter's moons, critics scoffed at the irrelevance. When Hubble revealed an expanding universe, skeptics questioned how it put food on tables. Yet history shows that fundamental research, no matter how detached it seems, often yields unforeseen ripple effects that transform daily life. The technologies forged in the hunt for dark energy, advanced optics, machine learning algorithms, even more precise medical imaging, frequently spin off into societal benefits no one predicted. Consider the Hubble Space Telescope itself. Built to study distant supernova and galaxy clusters, its optics revolutionized early breast cancer detection through sharper mammography. The same charge-coupled devices developed for deep space imaging now power smartphone cameras, while the algorithms designed to map cosmic voids help track deforestation and urban sprawl. The pursuit of dark energy isn't just about understanding the universe's fate. It's a high-stakes incubator for innovation, pushing engineering and computing to limits that later trickle down to hospitals, farms, and disaster response systems. But the ethical calculus goes deeper than spin-off technologies. Dark energy research is fundamentally a quest for context, to understand humanity's place in a cosmos where 95% of reality consists of invisible, unexplained forces. That knowledge reshapes priorities. Climate change, nuclear threats, and pandemics feel more urgent when we grasp how rare and fragile life-supporting worlds might be in an accelerating universe. Philosopher Carl Sagan captured this when he called planetary exploration a force of nature unto itself, arguing that cosmic perspective dissolves tribal divisions and fuels collective action on existential risks. Critics counter that such idealism ignores immediate suffering. A single dark energy telescope's budget, like the $10 billion Nancy Grace Roman Space Telescope, could fund thousands of hospitals or solar farms. Yet science funding isn't a zero-sum game. Nations invest simultaneously in particle colliders and poverty programs because societies thrive when they balance short-term survival with long-term vision. The same governments funding cosmology also spend exponentially more on military budgets or corporate subsidies, budget lines rarely subjected to the same scrutiny as pure science. Perhaps the most compelling defense comes from those on the front lines of both crises. Kenyan astrophysicist Paul Murden, who grew up amid post-colonial poverty, recounts how studying the stars inspired his community to value education as a ladder out of deprivation. Brazilian cosmologist Marcel Soares Santos, who splits her time between dark energy surveys and STEM outreach in Favelas, argues that cutting-edge research creates aspirational infrastructure. Telescopes and supercomputers become beacons that pull marginalized youth into science careers, diversifying the problem solvers tackling all humanity's challenges. The debate ultimately hinges on what kind of civilization we aspire to be. One that retreats from the unknown to focus solely on immediate needs, or one that dares to glance outward even while tending wounds at home. Dark energy won't cure malaria or stop wildfires, but the act of probing it reflects a stubborn human truth. We're creatures of curiosity, wired to seek meaning beyond our horizon. In doing so, we often discover tools and wisdom to heal the world beneath our feet. Dark energy isn't just a hole in our understanding of the universe, it's a glaring sign that the rulebook we've been using might be missing entire chapters. The standard model of particle physics, that crowning achievement of 20th century science, describes nearly everything we see with astonishing precision: the dance of quarks, the shimmer of electrons, even the ghostly neutrinos that stream through your body every second. But when it comes to dark energy, the model falls silent. There's no box to check, no particle to name, just a gaping void where an explanation should be. This isn't a minor oversight, it's a siren blaring that we're standing at the edge of known physics, peering into the unknown. Take the vacuum catastrophe, for instance. Quantum field theory tells us that empty space should be fizzing with energy, a seething froth of virtual particles popping in and out of existence. But when we calculate how much energy this quantum foam ought to contribute to dark energy, the numbers overshoot reality by a factor of 1 followed by 120 zeros. That's not a rounding error, it's the most embarrassing mismatch in scientific history. The only plausible conclusion: our theories are incomplete. Either something's cancelling out nearly all that vacuum energy in a way we can't yet fathom, or we're fundamentally misreading how quantum fields interact with gravity. This is where quantum gravity enters the scene, the holy grail of modern physics. Einstein's general relativity paints gravity as the curvature of space-time, while quantum mechanics treats particles as probabilistic waves. Both frameworks work flawlessly in their respective domains, but they speak different mathematical languages. Where they collide, like in black holes or the Big Bang's infancy, the equations explode into nonsense. Dark energy might be the canary in this coal mine, hinting that we need a unified theory to reconcile the cosmic and the quantum. String theory offers one tantalizing path. It posits that particles aren't dots but vibrating strings, and their harmonies dictate the laws of physics. Some versions even suggest dark energy could arise from extra dimensions, hidden folds in reality where gravity leaks away, weakening its grip on cosmic scales. But string theory remains frustratingly untested, a beautiful scaffold without experimental footing. Loop quantum gravity, another contender, reimagines space-time as a network of woven threads, potentially altering how expansion works at the largest scales. Then there's the bold idea that dark energy isn't a thing at all, but an illusion caused by our incomplete grasp of gravity. Modified gravity theories like MUND tweak Einstein's equations to explain galactic motions without dark matter. Could a similar adjustment account for cosmic acceleration? Preliminary attempts like the Einstein ether model introduce new fields that interact with gravity differently across vast distances. But these ideas often feel like patching a leaky boat with duct tape. They fix one problem while creating others. Perhaps the most radical proposal comes from holographic cosmology, which suggests our 3D universe might be a projection of information encoded on a 2D boundary. In this view, dark energy could emerge from quantum entanglement between distant bits of this cosmic code, a cosmic glitch in the matrix. Wild as it sounds, it's a testament to how far we've been pushed by dark energy's enigma. What's clear is this: dark energy isn't just a puzzle to solve within existing physics. It's a beacon guiding us toward a deeper theory that might rewrite our understanding of reality itself. Every telescope pointed at distant supernova, every supercomputer simulating alternate universes, every lab hunting for quantum gravity's whispers, they're not just chasing answers. They're chasing a revolution, and when it comes, it won't just explain why the universe is accelerating. It might reveal layers of existence we've yet to dream of. Saul Perlmutter still remembers the exact moment his skepticism turned to wonder. It was 1997, and his team at the Lawrence Berkeley lab had spent years chasing Type Ia supernova, meticulously measuring their brightness to gauge cosmic expansion. The data was messy, full of noise, until one afternoon, while staring at a graph of distant supernova, the pattern clicked. The ancient explosions were fainter than they should have been, meaning they were farther away than expected. The universe wasn't just expanding, it was speeding up. My first reaction wasn't excitement, it was terror, Perlmutter later confessed. I kept thinking, what if we've made a mistake? For months, his team rechecked everything: telescope calibrations, atmospheric distortions, even potential light pollution. But the numbers held. That terror morphed into awe when Perlmutter's rival team, led by Brian Schmidt and Adam Rees, reached the same shocking conclusion independently. The night Rees crunched the final numbers, he called his wife into the study, his hands shaking. "Either we've messed up spectacularly," he told her, "or the universe is doing something no one predicted." Across the globe, Australian astronomer Tamara Davis experienced her own revelation while analyzing supernova data in 2003. "I'd been trained to expect deceleration," she recalls. But the galaxies were fleeing faster, like they'd been given a cosmic push. One sleepless night in Copenhagen, Davis plotted the data on her laptop in a dimly lit hostel room. The trend was undeniable, a curve bending upward, not down. "I felt like I'd stumbled into a secret the universe had been keeping," she says. Her mentor, renowned cosmologist Brian Schmidt, teased her the next morning, "Welcome to the club of people who have lost sleep over dark energy." For Alex Filipenko, a key member of both competing teams, the breakthrough came with a twist of irony. He'd spent years arguing against the cosmological constant, convinced it was Einstein's folly. Then his own data forced him to reconsider. "Science isn't about being right," he laughs. "It's about letting the universe tell you when you're wrong." His team's observations of supernova in Chile's Atacama Desert, where the air is so clear you can see stars twinkle in daylight, sealed the deal. There's a humility that comes with Chinese letter ing paradigms. You realize the cosmos has a sense of humor. Then there's the quieter eureka of junior researchers like Maria Cristina Fortuna, who in 2018 spotted an anomaly in Baryon acoustic oscillation data. "I thought I'd botched the code," she admits, but her supervisor recognized the glitch as a potential clue, a slight unevenness in how dark energies push varied across galactic filaments. That's the thing about dark energy, Fortuna reflects. The biggest discoveries often start with someone doubting their own work. These stories share a common thread, the messy, human side of scientific revolution. Moments of doubt colliding with flashes of insight, rival teams converging on truth, and the sheer stubbornness required to question everything, even your own assumptions. Because when the universe decides to reveal a secret, it rarely whispers. It shouts in redshifts, supernova, and the quiet gasps of scientists staring at graphs in the dead of night. So here's a thought experiment for you. Imagine it's 50 years from now and headlines blare that scientists have finally cracked the mystery of dark energy. Maybe they've detected its quantum signature in a lab, or a revolutionary telescope has spotted subtle ripples in spacetime that reveal its true nature. How would that moment feel? A triumph of human curiosity, or just the first step into an even deeper labyrinth of cosmic questions? Now, let's bring this closer to home. Do you think we'll solve dark energy in our lifetime? Drop your vote in the poll below, optimist, skeptic, or somewhere in between. The answers might surprise you. Because here's the thing, this isn't just a yes or no question. It's a window into how we view science itself. Take the optimists. They'll point to history's pattern. Every generation thinks their puzzles are unsolvable until suddenly they're not. Newton couldn't explain Mercury's orbit, Einstein did. The atom seemed indivisible until we split it. Dark energy could be the next domino to fall, especially with tools like the Roman telescope and quantum computers on the horizon. Then there's the skeptic's view. Dark energy isn't just hidden, it's fundamentally elusive, woven into the fabric of empty space. Detecting it might require a theory so radical it'd make relativity look elementary. And let's be real, some cosmic riddles take centuries. Think of gravity. Newton defined it in the 1600s, Einstein redefined it in the 1900s, and we're still chasing quantum gravity today. But here's the twist, even if we never solve dark energy, the pursuit itself reshapes our world. The math behind cosmic acceleration birthed new branches of geometry. Supernova hunting algorithms now help diagnose diseases, and the sheer audacity of the question, why is the universe speeding up, keeps us humble, hungry, and endlessly curious. So cast your vote, but don't stop there. Tell us in the comments, what's your wildest theory about dark energy, a cosmic field no one's imagined yet? A glitch in spacetime's code, however far out, share it, because the best ideas often start as whispers in the crowd before they rewrite the textbooks. Dark energy remains one of the greatest puzzles in science, a force so dominant it shapes the fate of the cosmos, yet so elusive we can't directly see, touch, or measure it. Think about that for a moment. Nearly 70% of the universe's energy budget is tied up in something we don't understand. It's like living in a house where most of the rooms are invisible and the walls keep moving farther apart on their own. We've pieced together clues: the runaway expansion traced by distant supernova, the eerie uniformity of the cosmic microwave background, the vast void stretching between galaxies, but the full picture still dances just out of reach. The irony, the more we learn, the stranger the mystery becomes. Take the vacuum catastrophe. Quantum physics says empty space should fizz with unimaginable energy, yet dark energy's pull is inexplicably weak. Or consider the Hubble tension, where our best tools can't agree on how fast the universe is expanding. These aren't just gaps in knowledge, they're chasms, hinting that our understanding of gravity, quantum fields, even the nature of time itself might be incomplete. It's as if we've been handed a jigsaw puzzle where half the pieces are missing, and the ones we have keep changing shape. Yet this uncertainty is what makes the hunt so exhilarating. Every unanswered question is an invitation to build better telescopes, to rethink old theories, to imagine bold new possibilities. Maybe dark energy is Einstein's cosmological constant, a silent hum woven into space itself. Maybe it's a dynamic field like quintessence shifting over cosmic time. Or perhaps it's something far wilder, a signpost pointing to physics beyond Einstein, beyond quantum mechanics, beyond anything we've dared to dream. Here's the beautiful part: the next chapter of this story isn't written yet. The Euclid telescope, the Rubin observatory, next-generation supercomputers, they're all poised to peel back another layer of the mystery. And who knows, the breakthrough might come from a grad student staring at data in the dead of night, or an amateur astronomer spotting an anomaly in a citizen science project. That's how science works. The universe doesn't reveal its secrets to the arrogant or the impatient. It rewards the curious, the stubborn, those willing to sit with the discomfort of not knowing. So keep looking up, keep asking questions, because the day we solve dark energy won't just rewrite textbooks, it'll redefine reality itself. And when that day comes, you'll be able to say you were here, watching as the greatest cosmic detective story of our time unfolded. The universe is accelerating, but so is our quest to understand it, and that's a journey worth